Welcome back to the Calculus Analytic Geometry. So what we have been doing so far, we have covered the very fundamentals of differential calculus. In other words, that how we can, for a given, say, function, or a given relationship between independent quantities, how we can measure the various kind of rates of change. In other words, that how we can compute the derivatives, what were the techniques to compute the derivatives. Then we went into a lot of applications of the derivatives. So today we're gonna move to a completely new territory. Okay, it's not really completely new, but we have kind of, in some sense, already talked about it in our previous set of lectures. But it's a very interesting and kind of a new territory, the territory of the integral calculus. So we will now move towards what you call the so-called integral calculus. I mean, for the people who are kind of interested in, for example, Hollywood movies, or especially the animated movies, a lot of stuff that goes on in the animated movies is basically based on what do you call the integral calculus actually. So I will try my best to talk about that a little bit. Otherwise, I'm going to share some resources from where you can kind of get some motivation that that this new territory of integral calculus, how it is kind of a really interesting kind of stuff actually. Okay, so from where we will start? We will start from finding the areas. Now, finding the areas is really not a new problem. You have been learning this from very early stages of your mathematics education, but something that you have learned in your previous classes is more of that if you have some kind of what do you call regular shapes, like rectangles, like triangles, like some picture that is made up of rectangles and triangles, circles, you know how to compute their areas actually. But now we want to move into the new world where you can take really a complicated picture, and your task would be to compute the area of that picture actually. All this stuff, all this, the notion of what you call integral calculus, or calculus in general, was basically started by Isaac Newton and Leibniz actually. Especially Isaac Newton, he had a lot of what you call the astronomical data, but at that time there was no mathematics actually that can kind of explain that data actually, that can model that data. So what Isaac Newton and Leibniz, they both did, they kind of came up with some of the recipes of making sense of that astronomical data, and that recipe was basically, the set of recipes was the invention of what you call calculus actually. In particular, integral calculus. So for example, one of the problems that Newton was pretty much interested, anyone would be interested in actually, to finding the areas of different kind of complicated pictures actually. Now, we are used to of finding the areas, for example, of rectangles and triangles. For rectangle, I know that the area is length time width. For triangle, I know that the area is really 1/2 of base time height actually. Okay, this is what really the area of it is. And how do you, for example, get this area is that if you split, for example, a rectangle into two parts, so if the area of say this rectangle is length time width, the area of triangle is going to be the half of this length time width actually. So naturally, you should get some kind of this formula actually. That also, if you have this triangle, so this is like a base of the triangle, this is height of the triangle. So you multiply them and divide by half. So you're gonna get what you call the area of the triangle actually. Now, this especially what you call the area of triangles and rectangles, it is something of the very prime importance actually. Why? Because you can create a regular picture, okay, any regular picture, and you can try to find its area, for example, through the rectangles and triangles. In other words, if I give you a task, okay, so think very naturally, if I give you a task to find the area of this, so for example, this given picture actually, this trapezoid, okay, then how are you going to find the area of this trapezoid? You can pause the video and think for a moment actually. So if you have thought about it, one of the natural instinct of any human actually, let alone what you call the Newton, like this so this finding the areas is like a very historical problem. I mean, you see their traces in Babylonian edges. You see different kind of techniques of finding the areas of different regions are the parts of, so for example, fields. You find different methods in say Indian history. You find that in different kind of methods in Chinese history. So finding the areas is not a what you call new problem. So if you are encountering a picture whose area you don't know, then what would be your natural response to find the area of that unknown picture actually? The very natural response to find the area of an unknown picture or an unknown region is always to kind of break up into the kind of pieces whose area you know actually. Okay. So in other words, if you don't know the formula for finding, or if you don't know that how to find the area, a method for finding, for example, area of a picture that you haven't encountered, then what you can do naturally is to break that picture into something whose areas are known to you actually. So for example, if I want to find the area of this, there can be a lot of ways of doing it. There could be a lot of ways of splitting this picture, but for example, one of the natural way could be that, okay, let's split, for example, this picture into this rectangle and a triangle actually. So if you know the area of this rectangle, I mean, if you measure this, what do you call width and length, and then you can easily find what do you call the area of rectangle, and you can also find the area of what you call triangle. You sum them up and you get the area of entire picture actually. So that's what is the way that any sane person would try to compute the area of say given picture by breaking it down into the pictures or into the regions whose area you know that how to determine actually. So for example, if you take this polygon, then how you can find the area of it? You can split it in several ways. So for example, one way could be that, okay, you split it into the triangles. So this is one triangle, and this is another triangle, and this is say another triangle, and this is, for example, say another triangle and a triangle. So you split it the entire region into the number of triangles, and if you compute the areas of all these triangles, you can compute the area of this entire region actually. So you might be thinking that, okay, we know the areas of we know the formula for the area of what do you call a right angle triangle, but if a triangle what you call looks like this, which is not really a right angle triangle actually. But again, you can split such triangles into two right angle triangles actually. Okay, so the right angle triangles is really the basic building block through which you can take any regular picture. By regular I mean the picture that is made up of, for example, line segments actually, in which you have some corners, and so it has kind of a regular shape actually. So you're going to say that okay, you can split always such a regular shape in the terms of the triangles actually. Okay, in the terms of the triangles. Even when you see, for example, I mean, precisely this is the principle that also works when for example a person who want to create an animated, for example, character, okay, you want to make the face of it, for example, or you want to make some body part of that character. So if you take say for example face of the character, what actually is happening is that entire face of that animated character is being broken into what you call the small triangles. So you can approximate any kind of regular or irregular picture through the triangles, and even hence with the rectangles actually. So this is really the one of the basic idea if you have, for example, encountering the what do you call the regular polygons actually. So you're encountering the polygon, break them into triangles, and the areas of triangles, and you can compute the areas of any polygon actually. What if you now encounter, for example, such kind of a picture which is not really a smooth picture? So how you gonna find the area of such kind of picture actually? So if I say you, or before, for example, I reveal that how to find the area of such picture, just pause the video and think for a moment that if you have been given such a picture, such a region, and you have been asked to find the area of it, what would be your strategy of finding the area? Okay, our strategy of finding, for example, the area is going to be to kind of split this picture. Okay, split this picture in the kind of pieces whose area is known to you actually, or you have some formula for calculating it actually. Okay, so for example, I mean, you can do several things, but one of the natural things could be that okay, you create this rectangle and say this rectangle, so you can say now that this picture comprises of these three pieces. One is rectangle, I know how to compute its length and width, and other is really what do you call two semicircles actually, okay, with the diameter as this side. So if you can measure this diameter, then you know that the area of the semicircle or the area of circle is pi r square. So the area of semicircle is going to be pi r square by 2 actually. So this is pi r square by 2, pi r square by 2, and this is the area of rectangle. Sum them up and you get the area of this picture actually. Okay. How about if you have this kind of a picture? Okay. You are naturally tempted to, for example, break this down into two pieces. So one piece is really triangle, I know how to compute the area. The upper piece is, for example, a semicircle, so you know also that how to find the area of that actually. Okay, so in other words, breaking down, okay, the known picture, okay, breaking down the unknown picture in the terms of the what you call the known regions actually. By picture I mean these regions. Okay. So this is what is the really natural way of thought, way of thinking. So what Newton and Leibniz thought of, so they kind of attacked a very particular kind of a problem. That problem was very interesting. So they said that imagine you are sitting in this XY axis, okay, And imagine you have a curve actually. So I have this function, okay, and I want to compute the area, okay. So for example, using this curve, if I, for example, make a picture, okay, whose base is, for example, this this interval or this straight line, then this is really something that is different from a rectangle, because its upper side is irregular. The question is, can I find the area of such kind of a picture actually? And if we try to find the area of such kind of a picture, what would be the most suitable way or a consistent way to find the area of such picture? And this curve can be anything actually. So you can take, for example, this curve, you can take, for example, this curve, any curve. So no, these curves are really what you call y equal to mathematically f of x actually. Okay, the question is, can I have a consistent method for finding this area? Okay, can I have a consistent method for finding, you know, such areas? This is the fundamental question that Newton and Leibniz basically asked. And then they developed some tricks actually. So first I would like to invite you to say, think about your own strategy. So pause the video for example, few minutes, and think about that. If you haven't given such pictures, what would be, you know, your way to find the areas of such pictures actually? Okay, you know, so these all are the areas whose top is really a function actually. Okay, whose top really is a function y equal to f of x. Okay. Now, I can do several things. I can, for example, take different, say, known pictures, and I can, so the intuition comes also from what you call what you saw here. Can I break these pictures down into some pictures whose areas are easily computable actually, okay, whose areas are easily computable? And the answer is, what picture you're going to choose actually? Are you going to choose, for example, circle? Do you like to fill this with circles actually? Okay, so one possibility could be fill this entire picture with circles, okay, and if you are filling, for example, this entire picture with say 50 circles, then you're going to say that, okay, you know, the area of this picture is approximately equal to the area of 50 circles. But this would be an approximation. Okay, this would be an approximation. Why? Because there are always going to be areas which you can't fill through what you call circles. Okay, circles. That could be one of a way to doing it. You know, one might think, okay, what if instead of putting a lot of big circles, I try to put say small circles actually. Okay, instead of putting say big circles, let's put say tiny circles and fill this entire picture with tiny circles actually. Okay, so fill this entire picture with the tiny circles. Okay, and then, you know, count the circles, and then, okay, whatever would be the area of, say, for example, whatever is going to be the number of, if they are circle of the equal size, whatever is going to be the number of the circles, the area, this area is going to be the area of these circle multiplied by the number of circles actually. Okay, this could be one of a way of doing it. You can also try to, you know, what do you call, fill this with say rectangles. You can also try to fill it, for example, with triangles. Okay, so you have a different possibility of what do you call triangulation of this region, or splitting it into the circles and splitting it into the different kind of known pictures actually. Okay. But we want to talk about really what do you call the trick, for example, that Newton and Leibniz thought of actually. Okay, so they thought of very interesting and a simple trick. Okay, and the trick was that take for example the rectangles of equal size. Okay, so take some rectangles. So let's take some rectangles and let's make some copies of it. Okay, and put these rectangles at different places, and then sum what do you call the sum the areas of rectangles actually. So whatever is going to be the area of rectangle, that is going to give you kind of an estimation for the rectangle. But for example, if I take such a rectangle and put at different places, one here and other here and other here, 3, 4, 5, 6. So you're going to say, okay, there are some places where these rectangles are not going to cover the part, and there are going to be some places where if I put, for example, take this rectangle and put it here, is going to over, what do you call, these rectangles are going to cover kind of more and more areas actually, more area than the given picture. Okay, so let's put the rectangles. So what is the recipe of putting the rectangle? The recipe of putting the rectangles is that, okay, split the base of the picture into the pieces, 1, 2, 3, 4, say for example 4. Okay, and try to fit, for example, a rectangle. Now the question is, what should be the size of the rectangle that we should put here so that I can kind of approximate it. Okay, let's put another rectangle. So what should be the size of the rectangle that we should put here so that we can, fill this picture with the rectangles actually. So I mean, there can be a lot of tricks actually. For example, one trick could be that, okay, say if in each, for example, this piece, in each, say this interval, take for example this right end point and see what is the output corresponding to this right end point. So if this is input, then that is the output actually. I mean, if this is representing y equal to f of x, okay. So if this is input, this is output actually. So take the right end point and make a rectangle. Okay, so I made a rectangle out of right end point. So I took, for example, the right end point from here and made a rectangle. And then I took, for example, the right end point from here and made a rectangle. I took the right end point from here and made a rectangle. I took, say, the right end point from here, okay, and made the rectangle. Right end point, what is the corresponding output? And made a rectangle. And the right end point and corresponding and made a rectangle. Okay. Now you can say that the areas of these rectangles are really giving you a pretty nice approximation of this entire area. But there is some trouble with, obviously there is some also trouble with, for example, putting these rectangles here actually. That there are some places which are not covered by the rectangles, and there are some places, for example, this and this part are not covered by the rectangles, this part also, but there are some places where these rectangles are over covering the area actually. So they are adding what you call this additional area. So therefore you're gonna say that, okay, I mean, so there will be error in this rectangle, this what do you call picture actually. Okay, there will be error in this picture. So again, if I would say that pause the video for a minute and think about it. What should I do with this rectangles so that these unfilled areas or the overfilled areas, this error, okay, this error, we can kind of minimize this error actually, okay. We can kind of minimize this error. So what should be done? What should be done? So you may think about it for a minute actually, and then we can move on to different parts. Okay. So, for example, one strategy that someone can adopt is that, okay, instead of taking the big rectangles, let's split these rectangles into some more rectangles actually. Okay, so let's take, for example, make some more rectangles actually. Okay, some more rectangles, and let's see what happens then. Okay, so I'm making new pictures. Now I have kind of more intervals, the more bases of rectangle. For example, now in this interval, if I take the right end point, okay, and compute the area, I'm getting something like similar. Again, taking the right end point, getting something like similar. Taking the right end point, so this is end point and this is output of it, and I'm getting what you call something similar. But now you can see that by shrinking the size of the rectangle, okay, here you still have a trouble, but here you have substantially. So previously this big rectangle included a lot of extra area, but this small rectangle, blue rectangle, now includes what you call less area. So it includes less area. So okay, it's including some area, but it's less as compared to this big chunk actually. How about now, for example, I take this interval, okay, so I kind of substantially reduced the area, and then, for example, what you can do is that, okay, so take the left hand point, right hand point, create the more, take the right hand point and create a rectangle, take the right hand point, create the rectangle, take the right hand point, for example, and create the rectangle. Okay, so it's going to be this actually. Take the right hand point and create. You can see that now, like, okay, this, so in the big white rectangle, okay, the big white rectangle, there was a lot of space left actually. But if I broken this big rectangle into two small rectangles, now the area is being, what do you call, the left area has substantially reduced actually. For example, okay, now you can see that, okay, like this rectangle is covering, a lot of area, but there is a big chunk which is, this rectangle is not covering actually. So now let's take, for example, the right end point, for example, at this point. So it's going to be some point here. So if I make a rectangle, you can see now that now this blue rectangle kind of included a lot of area actually, which was left by the right, this the big white rectangle. And now, similarly, for example, in this rectangle, if I take the right hand point, it's pretty small area now that has been left now. For example, I can take now right hand point and create a rectangle, okay? So you can see really a tiny part is remained, and similarly I can take a right hand point and I can, what do you call, you get this area. So now I can say that if I compute the areas of these blue rectangles, which is easy to do, length multiplied by height actually, or width multiplied by height, okay, and sum up the areas, these blue rectangles are giving a good estimation of this unknown area than the white rectangle actually, than the white rectangle. Why? Because the white rectangle has big sizes.